Alright, so now that we've seen the basics of GLSL and shading, we're ready to start doing physically realistic models of lighting. So we're going to use the shaders to actually light things and make them look like they might look in a real world scenario. So if you recall, our shading so far, at least at the vertex level, has been pretty simple. So when we were doing this triangle, we had 3 vertices connected by one triangle. And even when we were doing these more complicated animations, we really relied on the fragment shader to do the heavy lifting. So here we still only had 4 vertices and 2 triangles, and we just had a lot of pixels in between those 2 triangles that were shaded by the fragment shader. But now, in this module, we're actually going to, for a moment, have the vertex shader do some heavy lifting. So just to give you an idea, if I go to this scene has a lot of vertices in it. So in particular, you see all these vertices on the cubes and the rectangular prisms. You see the vertices on the ellipsoid and on my head. And so actually now the vertex shader is going to be doing more work. Okay, so we got a lot more vertices that we're sending there. And the shading happens when we connect these vertices with triangles. So you see, for example, this cone is made up of a bunch, it's approximated, it's not a perfect cone, but it's approximated by a bunch of triangles connected to each other. You got these 2 vertices on the base and 1 vertex at top. You can see a similar thing on the ellipsoid here, a bunch of triangles stitched together. And on my head, you can certainly see a lot of triangles as well. So that's how the shading is going to happen. So the fragment shader still has a role, but we have more processing to do on the vertices first because we have many more vertices. Okay, so that's what our scenes are going to look like. So the vertex buffer is going to be doing more work. And now the question is, how do we get these effects that we're seeing here? So notice the shininess, right? As I move around, this sort of the light is shining off of the surface here. I can also see that closer to the center of the light, it's brighter, and as I go out further away, it's darker. I can see that the lights are lighting the front of this cone and the front of the cylinder, but not the back. And same thing with my head over here. So how do I get those effects? So we're going to start to come up with some physical models of what happens when light bounces around. And we're going to see if we can translate those into math and then into code in the shader, in the vertex shader, okay? So we're going to be talking in this first part about something called Lambertian Illumination. So we're talking about local illumination. We're just going to focus on one light at a time for now. Even though this scene had 2 lights in it, we're just going to back away and think about what does one light at a time do. But even before we do that, there's a very simple model for shading that we can come up with, which is, I guess I'll call it just flat shading. So this is where you say every material in your scene has a constant color. And I've said it's a vector because every color has a red, green, and blue component. And so does every material. So every material is going to have properties, each of which has a red, green, and blue component. So we call this here the ambient component, K sub A. And just to give you an idea of what that might look like, here's a scene that has only the ambient component. So we've got a green color, a red color, and a yellow color on different materials. And so yeah, I mean, you certainly have the perspective here, you can make things out, but there's a lot of geometric detail that's lost. So there's no effect of this light on everything, so everything is colored exactly the same. And so for example, I can't even really tell from this angle that Homer has a mouth. I can see his silhouette, but everything's the same color, so there's no contrast there. If I go to the side, I can kind of see that, but now I don't even really know that he has fingers, right? So that sort of thing. So this is clearly not enough. I mean, it's a start and it's pretty simple. You just set, the vertex color to be exactly the material color, and then the fragment shader will just, interpolate that to all the pixels. But we should be able to do something a little fancier than this. So this is where Lambertian illumination comes in. And sometimes I'll also call this diffuse illumination. Because the assumption behind Lambertian illumination is that your materials will reflect light that's coming into them equally in all directions. So this is a simplifying assumption, but it's actually pretty realistic for a lot of materials in the real world, like corrugated surfaces like wood And also I have this table here that's all black and it's diffuse. So basically the opposite of a mirror. It doesn't have a preferred direction. It just takes light in from the light and it reflects it out in all directions, maybe scaled down a little bit. So if I have a red material, it'll only reflect red light back, for example. But it'll do so equally in all directions. And that's going to make things a little bit easier to start with. So let's think about that. So we're going to have to think about light coming into a surface. So let's put a light here. And we'll consider a bunch of rays coming from that light that go onto the surface. Now, I'll have the normal to the surface, which is important because I really need to know, as you'll see in a moment, I need to know the direction of the light with respect to how this material is oriented. Okay. So I'm going to assume that everything is locally flat and kind of deal with them as planes. And we'll talk more about that, how to deal with that later if they're not planes. But, okay, so here's the light that's coming straight down, right? If I were to be sunbathing at this location right here, I'd probably get totally sunburnt, right? So light coming straight on is very concentrated. But by contrast, if I take the light rays and I rotate them by some angle, what I see actually is the same number of rays actually covers a larger area. So it's less dense. So just to draw it on here, see these rays take up this much area, the original ones. They take up that much. Let me make that nice and big there so you can see it. But these rays, actually the same number of rays, but coming in at an angle, you see they take up a larger area. So that's actually less light coming into this to a volume. So actually, and if you look at this original here, you see that when it's straight on, there are 6 rays coming into it. But when it's at this angle, there's only 4 rays coming into it, right? And those 6 rays actually end up covering a larger area. And the effect only gets more pronounced the more I rotate it. So if I start again, and I rotate this, let's rotate it like really at quite an angle. So this is like almost at sunset. And look how much more area these 6 light rays take up on the same material. So they take up that whole, so more than twice at this point. So this is why you don't get sunburn as much later in the day. And this is also why, because of the tilt of the Earth, that we have winter. Because the sun never gets head on in the winter. So that's why. It's not because of the distance of the Earth to the sun, it's because of the tilt and because of this property. So let's try to mathematically derive, well, can we come up with an expression in terms of the angle of incidence with respect to the normal of how much light is actually going to get absorbed per unit area? Okay, so that's what we need to do here. And I'll keep this picture here just so you can see it, but I want to draw another picture over here, just considering 2 rays next to each other, because that's all we really need to derive an expression. So what I'm going to look at is 2 rays which, if I draw a perpendicular between them, I'll say, okay, head on, they would be at a distance of d from each other. But what I'm interested in is when they hit the surface, there's actually another distance, and I want to know, okay, what is this distance between the 2 rays when they come in at an angle? I'll call that distance p. Okay. So what I can look at here is just actually some basic trig. So what I can look at is I can say, okay, well, you see here, this is the angle that it's been rotated, right? Actually, let's be more careful. So that's not true. So let me say, actually, this is the angle that has been rotated. So I'll call this angle A. So you see, if A is 0, then it's head on, right? That's like rotating this back this way. But here, we've actually rotated it away a little bit. Now, let me actually just do a little bit of simple geometry. So I'll notice that this is a right triangle here. And so what I can say is that this angle here is 90 minus A. And then I have a reflex angle over here, so this is also 90 minus A, this angle. And I can make another right triangle actually. So I'll just copy that D here. So I'll consider another line segment which is parallel to that one. So this is the shortest distance between the two lines here, D. So that's when they're head on. But I want to know what's this segment length here. So P. And then this is a right triangle because again this is the shortest distance, so it's a perpendicular between the two. Okay. So here we go. So this is a right triangle. Now I have another complementary angle, and I can see that actually this angle here is A. And that kind of makes sense, right? So the more that I rotate this, you see the more this comes away from this. Okay. So now it's just a basic trigonometry problem actually. What I can see is that D is an adjacent angle here in this right triangle. So we can see that D is equal to P times the cosine of A. And if I rearrange that, I can say that, well, then P is equal to D over the cosine of A. Okay, so that length gets longer. But actually, we're interested in the density. We're interested in how much light is absorbed per unit area. So we really want the reciprocal of this. So we really want to know, well, what's 1 over the length? Because that's going to tell me how many rays come in over a unit area. So if I just take the reciprocal of both sides, I say, well, 1 over P is equal to cosine of A times 1 over D. And 1 over D is really the original density of light. So that's like sort of the most dense you can have, 1 over D. D is the smallest number you can have there. So this is the original density. And this is the final density at a particular angle, A. Okay, cool. So what we see is actually the density, the intensity of the light falls off as a cosine in the angle. Okay, so this is like a very important thing, and this is how how the seasons work, right? So if I zoom back out, well, okay, so I had some light rays coming here. So let me actually draw those light rays at the angle that they're really coming in here. So let's see, let's try to get this right. So it seems like, yeah, they're coming in at about that angle here. Okay. Now, and let me just look at the one that's going straight into the surface. Okay, so what I can see is this has the angle here that I'm looking for, the angle of A, right? So this is my angle A here. And so what I really need to look at is, so I have this vector n and I have another vector, so let me call this L. So this vector L is the vector from the point of intersection on the material. So we're just looking at a particular location on the material. It's the vector from that all the way up to the light. Okay, so we'll call that vector L. But actually, if we have a normalized version of that vector, so I'll call this L sub n. So let me finish making it here. So if I have a normalized version of this vector, ooh, that's kind of big. Okay, so I'll call this L sub n. So it's in the same direction as L, but it's normalized. So now what I can say is, well, Ln dot n, so Ln dot product with the normal is equal to the magnitude of Ln times the magnitude of n times the cosine of the angle between them. Well, guess what? They're both normalized, so that's just going to be the cosine of A. All right, cool. So what we can do is we can get the factor that this thing scales down by as a dot product of the normal direction and the direction to the light. So the final equation for diffuse shading is as follows. So for diffuse/Lambertian shading, what we have is this equation. So we're going to keep the ambient term there. So we'll still have a Ka. But now we're going to also have, okay, the color of the light. So I'll say that Cl is the color of the light. It's RGB. And so it's going to be the color of the light, whatever is the incoming light color, times a material diffuse coefficient, so that's Kd. So that's going to tell us how the material reflects light. So it's reflecting equally in all directions, but it doesn't have to reflect all the light. Like I said, it could be a red material, it could be a green material. So that's how much it's going to reflect back. But we also have this term n.ln, so that's going to get us to fall off as a cosine. So we got the ambient material plus the diffuse material. So let me label them here. So we got our ambient, and we've got our diffuse. And so that's all there is to it. And so once you incorporate that, you look much nicer. So now I can actually make out geometric details. So one sort of caveat that I do have to be careful of, though, is I don't want this to go negative. So if my light happens to be behind my scene, so let me flip this the other way. Yeah, so if I have a light that's sort of behind my material, then you notice that this direction vector Ln, so this is the Ln for that light. Ooh, that was huge. Okay, hang on. Notice that's going to make an angle greater than 90 degrees with n, so the dot product will be negative. But we actually don't want to light things on the back side of this at all. We only want to light things on the front side. This is why I had you do the above or below thing before. So there's one caveat. We'll say if n dot ln is less than 0, just make that 0. So make the whole coefficient 0. Okay, so that's the one caveat, because we don't want to light the back faces. We only want to light the things that are in front of the light. So if I look on the back side of Homer, I only see the ambient color now. I don't see any diffuse color. Okay? All right, so that's all there is to Lambertian shading. But now I'd like you to try to implement Lambertian shading yourself. I've provided a lot of code for you, but I want to show you. So I want you to do this in a Vertex Shader. So if I go to the first exercise, you'll see that I've started you off with a bunch of code. You don't have to edit the scene. The scene is just, actually you can't. I disabled editing. It just has Homer in the box and all that. And you see the Fragment Shader is quite simple as well. So the Vertex Shader is where we're going to be doing the heavy lifting here. Now, so what's going to happen is we want to come up with a color, and that's going to be a varying. So we'll compute a color at each vertex from how that vertex is lit by the ambient and diffuse terms. And that'll be passed on as a varying over to the Fragment Shader. And that will just be interpolated by barycentric interpolation between the vertices. Okay. So we're really going to focus on lighting the vertices themselves. Okay. So I take care of a few things here. In the scene, there's a composite transformation matrix that could happen to a vector. So this is the original position of the vertex. But again, there's a transformation matrix that you might have applied in the scene. So I do that multiplication using homogeneous coordinates. There's also something called a viewing matrix, which we'll talk about more in a couple weeks. But it's that this thing is placed somewhere in the scene, but also my camera is looking at it from a certain angle. So I have to do one more transformation actually after I've done that original transformation. And then there's something called a projection matrix. So this is the viewing matrix that gets me into the camera's coordinates. And this is a projection matrix, which actually we'll also talk about in a couple of weeks. This flattens me to 2D. So I have my three-dimensional coordinates, but this is actually what's going to give me a position on the grid, that grid -1 to 1, -1 to 1 that we talked about. And the last thing is, remember, we actually have to have a special matrix to transform the normals by whatever transformation we're doing to this material, to this shape. So that's called the normal matrix, and I also pass that along. Okay. So I know what the normal is now, which I need to know, again, to determine this angle, right? I need to know the normal of the surface. So I need to get that transformed properly. I know the position. I'm going to pull out just, this is in homogeneous coordinates, but I'm just going to pull out the x, y, z, so I'm going to call it vpos. I also know the position of the light, which I need to know to construct this vector, right? So I'm going to pull out the position of the light. By the way, there's actually an array of lights. We'll deal with that later. Right now, I'm just focused on local illumination, so one light at a time, so I'm just going to look at the first one. And now I have, okay, and then I also have this diffuse coefficient, right? Actually, yeah, it's UKD. This is uniform. So I've got my diffuse, my material UKD. So that's this KD here. V color, that's just an extra thing. You can kind of ignore that. It makes it so that if you want, you can specify different colors at each vertex, but you could ignore that. And then this is the coefficient that I need to compute. So this is going to be the n dot ln clamped to 0 appropriately. So what you need to do is just set up the vector from the position to the light, take the dot product of that vector with the normal, and then do the multiplication here. Okay, so the multiplication is actually already taken care of. So all you need to do is compute this, set up the vector right so that it actually computes the right dot product, and make sure you clamp it to 0. And once you do that, you'll transition from a picture that looks like this to a picture that looks like this. Okay. And I give a lot of hints. There's a lot of common mistakes doing this. So when you're finished and you've read, I mean, you can check at any time by just clicking Update Shader. So watch it. I could do something like, you know, maybe I scale the ambient coefficient by 2.0. You'll see everything gets a little brighter. If I click Update Shaders, there we go, everything got brighter. I'm not done yet, but if you want to check, it'll give you a hint. So you can check at any time. There it just tells me try again, because that's not a very common, just shape, you know, ambient by 2, that's not a very common thing to do. But if I went back to the original, oh, I thought it was going to tell me a hint about ambient. Let me try that again. So if I refresh and now click submit, oh, I forgot to do the ambient check. That's okay. Anyway, but there's a lot of common mistakes and it'll tell you. So you can check here. If you get it correct, it'll give you credit on Canvas as usual. All right, so that's Lambertian shading. So give that a shot, and then we'll talk about another kind of shading.